Let's check. The cylinder can be described using x, y, and z first. So x and y and z. We know how to do that. In 2D, x and y gives you a circle. What kind of circle? Radius 2. So it's 2 cosine theta and 2 sine theta. Does it make sense? How would we describe z? Z going up and down forever. So we're going to keep z as a parameter z. That's going to be an unusual thing to see. We could call t if you want, but usually actually people don't do it. There's no necessity to introduce one more variable if z is just anything possible. So we're going to keep z as a free parameter going from minus infinity to plus infinity. From here, we're going to describe this surface using only 2 parameters. R now does not depend on t. We could call this t, but R depends now on 2 variables. The angle gives you how wide the cylinder is, and height will be described by z, how tall it is. This will be described using a vector, because remember a very long time ago, a century ago, I was holding a laser in my hand. I was showing you that a vector is like a laser. It points in things, and when it points in things, it keeps describing the surface. So we're going back to this idea that I'm standing and I'm pointing from 0, 0, 0, right? And I'm pointing at this, and then when I'm pointing with the vector, it keeps running whatever way it's running. And while it's running, it describes this shape we are looking at. So let's point with the vector. A vector is pointing and describing a rotation, how big the rotation is. 2 cosine theta and 2 sine theta big. Cosine and sine makes a circular rotation. 2 makes the size of the rotation. And the third variable will be height. Height, how tall this bottle is. Z tall. Now let's see if everything here is infinite or not. We all agreed, well, I will ask you in a second if you agree, that z is infinite. It was never restricted. So it's from minus infinity to plus infinity. It will go infinitely up or down. So this is an infinitely tall bottle. But theta is restricted from 0 to 2 pi. So it has 1 full rotation. You can have multiple rotations, but it's just not necessary. And this is how we describe a cylinder. It looks like whatever we learned before, so it's kind of hard to see what is new about it. The new about this is that now R never been 2-dimensional before. We always had R of t, if you remember. dr was R prime and stuff. Now R has 2 variables, u and v will be always different, and that's the creativity of each problem. You'll see different examples right now. So this is the most important part here, describing the shape, and then putting restrictions on that shape below it. So we're describing the shape as a circle in 2D, right? Radius 2, with the height, and the height makes the circle growing up and down forever, which makes a tube, and the tube is a cylinder. Does that make sense? It's a weird combination of the old knowledge and new knowledge, and that's why it's a bit sketchy to see like what is so different here. But the more we're gonna work on the examples, the better it gets. One more famous example, or not famous, just known or typical example, is a sphere. Let's figure out parameterization of the sphere. Yes?
So the u in this case is our theta, and that turns into 2 components?
Yeah, exactly. U and V will be a creative choice that you should choose. We could parameterize differently using, say, spherical coordinates. Phi, theta, and r. Too complicated. So this one we could shrink only to 2 dimensions. So parameterization is pointing with your laser, I think that's why it's a vector, right? Pointing with your laser and making as minimum dimensions as possible to make it convenient. And that's what sometimes people describe some behaviors with 25 dimensions. There's a whole cool theory that teaches people how to decrease dimensions. And that's what we decrease to 2. That is very nice expression here. 2 dimensions on. Yeah.
And does the order matter?
Good question. No, this is typical order. Angle goes first usually. Good question. You describe, you derive, you show the order and then show how they're restricted. So not really. Yeah, that's a creative process. You will be basically creating shapes by yourself. And usually it's either alphabetical or known figures. So theta is more known than phi. R usually goes first. X, Y, Z usually goes in order. So yeah, it's creative, but some kind of standards are there. A sphere. A sphere x squared plus y squared plus z squared equals 9. 3 variables are here. It's a restriction in 2D. On the floor, it's a circle. In 2D, but on the other floor, because there's 3 planes, right? It's also a circle, and on this one, it's also a circle. So circles from all sides gives you a sphere. It's rotation from all direction, and the only restrictions is the radius equals 9 or 3. 3. So to describe point everywhere, what kind of parameterization will fit any point over here? Originally, point was described with 3 variables x, y, and z. We're gonna use u and v. But which kind of u and v? So let's make a choice. And one of the choices is to use spherical coordinates. Spherical coordinates here will say, well, we technically speaking will show, as you can see in the previous example, radius is hidden over here. Somehow radius was not even in the picture of the list of the variables. That makes sense because radius is fixed. Radius is 2. So we're going to do the same thing here. We will show a reader that the angle around is changing and the angle above is changing, north pole versus south pole, east and west. But the radius is fixed. There's only 2 variables here actually, with the radius r3. So let's do that and then I'll answer some questions just a second. Let's do that to have a big picture done. X, Y, and Z. How do we describe a sphere? Using spherical coordinates. Spherical coordinates. We know equations. Hopefully you remember equations for spherical coordinates. 3 is the radius. First 3 cosine theta and 3 sine theta. But each has also what? Sine phi, right? See, I remember it. No, I always say, if I remember it, you definitely can remember. Most of the people have better memory than me. And then this one will be cosine phi, the one that's missing. That's how I memorize it. So we know spherical coordinates, right? Here they are. Let's convert this into 2 dimensions. Only using theta and phi, because r over here is a fixed number, so we don't need that dimension. Then it becomes r that only depends on the angle spinning around, and the angle with the z axis, which we don't even see here, can be described with a vector. The first 2 components, we're just gonna list all of these components because it's basically all done already. We're going to have 3 cosine theta. Okay, it's going to be a very long vector, so let me have enough space. You list all of this, like so. R of theta and phi, just depends on 2 variables, will be, the first variable is r sine phi, cosine theta. Well, I changed the order, doesn't matter. 3 sine phi, sine theta, comma, 3 cosine phi. So it's my x, y, and z. Now, it is a vector r, points at the sphere, like it points at the basketball ball, right? It's only outside of it, and it scans it outside and tells you that x, y, and z are described this way, where theta is fixed, a full rotation from 0 to pi, and phi is also having full rotation. What is the full rotation for phi?
0 pi.
0 pi. And that's how we describe surfaces. R now, this vector that points at things, it's always been like that. But now it's a 2-dimensional vector, so we're going to upper dimensions here to describe surfaces. What was your question? Questions, what do you think? And then more generally over here, right down below, there's a table. More generally for the function z that depends on two variables, we can use r, x, y, and that z that has a third variable. A z is a third coordinate that depends on two previous ones. That is the general case. You will see it. So surfaces are more general than functions. That's kind of the idea here. Surface. Function describes something. Surface is a three-dimensional object, so it's been described as x, y, and z in Cartesian coordinates, or cylindrical coordinates. Z is the height with a spin, or spherical coordinates, a spin around and a spin to the North Pole, like so. That is a spherical coordinates. So we have several types of coordinates now to use to describe surfaces. And we're going to do more general case right now. What do you think about that? This topic is challenging from one typical point of view. When you see me doing this, it makes sense. But the moment I will ask you to do it on your homework without any instructions, that's when people stuck. So be okay with that, post it in the forum, and help each other. And then on Monday in office hours, I will help you as well. But that's going to be a challenge. When you actually ask to do it and you're like, okay, she told me it's going to be creative, and that's when you stuck. Like, how would you start? Start with something you know. Polar coordinates, Cartesian coordinates, write down whatever you know. We usually know this part. We know this part, or we usually at least know this part. Something we know, and then from there, try to move on. Solids of revolution. Look at that. Do you remember we used to do revolution? No. That was Calculus 2 class. Calculus 2 class, it was teaching us how to find volumes using shell method, watcher method, and that kind of stuff. Finally, we're gonna do it. Well, we already taught you how to do it without it, but let's do it again using parametrization of the surface. Parameterize surface obtained by rotating the curve y equals 1 over x between x equals 1, x equals 2 about x-axis. Such a nostalgia. It was long time ago. Calculus 2 class, second exam. Who failed it? Raise your I'm joking. Let's do it. Let's do it together. Solids of revolution. But you have to say, especially as an engineer, lots of things are created from revolution, so it makes sense they're teaching this. I was never taught any of this, so I had to learn myself when I was teaching it in the United States. So here's the picture. The picture is a function 1 over x. This function goes above x-axis, right? X is not 0. Then it's revolving about, I usually have notation like so in my classes, about x-axis. So it creates a mirroring function below, and then you create a nice looking shape looking like that. It's infinite, but then you have a cut. The cut says cut from x equals 1 to x equals 2. And that's how the shape becomes finite. We were teaching you that you need to find a slice and then use a washer method, blah, blah, blah. In this case, we're going to finally do it the normal way. The normal way is to create a three-dimensional Cartesian system. It's nice to know that you can rotate Cartesian coordinates the way you like it. Z is not necessarily always going up. You can first create yx, and then z will be the perpendicular one to those two. Or you could create it like so. If you got used to this notation in this class, x and y, then it will be rotated above like so, right? So it will look something like that, and then z goes up. It's just harder to draw it, but technically speaking, this is what we're doing here. But you know, it's actually a pretty creative process. You can put x, y, z any way you like. You're supposed to know the slice. That is still the case. We were teaching you slice describes the object. This is the slice. We're gonna describe it in 2D. The slice is a circle. The slice is a circle. What kind of circle? It is described with other two variables. X is fixed, but X is fixed. This slice is shadowed into or onto ZY plane. See? So the slice is located on the plane. Let's call it Z and Y. That's a pretty cool idea here. Well, actually, they do it the other way around. Y and Z. I can see it from the input. Y goes first, and let's put Y first. So this slice goes to the direction of that plane where X is fixed. Because the slice is parallel to the wall on the left, whatever slice is parallel to that variable, those variables will be used. X is fixed. What is the radius of the slice? The radius depends on the function. Slice is much bigger over here and much smaller over here. This function dictates the radius, and the function is called 1 over x. So the radius is 1 over x. Does it make sense? We had this before in calculus 2, actually. Let's stop jumping. So the interesting part here is this next step. The next step when we start describing it. How would we describe this shape? Well, now we know there will be circular motion with z and y involved. So y and z now will be described using a polar equation, not even spherical. Those are polar equations, right? We know how to describe polar. We know how to describe circles in 2D using r cosine and r sine. In this case, you just need to be careful. It's not x and y anymore. It is y and z. That's a pretty creative part, having 3 dimensions. Imagine having 17 dimensions. That is the one you cannot imagine until you make slices. When you make a slice, you see things. So for example, if this is a bacteria that cannot fly, bacteria only see everything in 2D. The moment you made a slice and put bacteria on this slice, which is looking like a petri dish, bacteria sees only this world. Bacteria doesn't know that there is a height of this world called x. So it makes sense that at any slice you decrease the dimension. The more slices you make, the more less dimensions you have. R cosine theta and r sine theta, we know that. R is a function. And the function is described as 1 over x and 1 over x. Cosine theta and sine theta. Very interesting that radius now depends on the interesting, today it's just doing that. Depends on the function. For this particular case, for x and for y and z, x is fixed. For any different x, the circle will be bigger or smaller. So different x. Make sense? Larger x. Actually, the larger the x, the smaller the radius, because it's 1 over x. So, like so. So, the idea is, you know what? Let's keep x as a parameter. And this is the notation we'll be here using. Start with calling x, just like z used to be a parameter, the very first example. X now will be a parameter. This notation x equals x means we're denoting. Do you do coding in your life? You know this notation? Isaac is like, yes, I know this. What does it mean?
It means the value of x is assigned to...
Assigned, right? So it's assigned or called. So we could call it some other name, say t, time, but we don't have to. There's no need to introduce any new number, variable, letter. T will be changing, yes, but t equals x, so let's keep it as it is. We're calling x to be x for this description of the surface we have. But x is fixed between 1 and 2. They told us that. They told us that x is fixed between 1 and 2 about x-axis rotation. So now we have this. We have this parameterization, that's the beginning. Y depends on x, which is a parameter, and theta. Z depends on x, which is a parameter, and theta. This is what we're getting from the slice. Thus, R is a collection of these two. Thus, remember that R is a vector that collects x, y, and z. We had this on the test as well. When you describe x, y, z, or just x, y, R collecting them. So R will be the first variable, second variable, and the third variable. It's a 3-dimensional object. what is the second variable? It's y. Y is 1 over x cosine theta. So the second coordinate, y coordinate, is spinning using cosine rule with the radius 1 over x. The third coordinate is spinning using sine function and the radius 1 over x. What is the first variable doing? Changing as x. Sometimes in the book you will see it's t. That is also common, but again there's no need for that. So very commonly you will see this notation x equals x. That means we just deciding to keep x as a variable and use it as a parameterization, like so. That's a very unusual thing for when you see it for the first time, and then you get used to it. X is restricted and theta is restricted. X is from 1 to 2. That makes the object finite. So it's a finite tube. Well, it's like horn. And rotation is from 0 to 2 pi. And that concludes the description of the surface we were looking at. More generally, it looks like this. Let me move this. Write this down. More generally, if you rotate the function f of x about the x-axis, you keep x as the variable because x will be the variable of the rotation, x-axis rotation. Theta will be the angle, how much do you rotate. And then you start describing it. How do you describe it? X is you chose it as a variable. Cosine and sine is the rotation. Radius will be that function that creates shape of the rotation. So in this case it was 1 over x. It can be literally anything else, maybe exponential function, and it will look like this, right? Maybe it's like some kind of wiggling 1 over sine, right? So that function dictates the radius, and that's why r cosine and r sine becomes f of x cosine and f of x sine. This is kind of a more general formula how to do it. When you rotate it about y-axis, redo the whole thing using y as a parameter, and so on. Did you get any of this?
Yes.
Howdy. Good job, people. Yeah, that's totally. Anyone else here from Texas? Anyone show up from Texas? We don't have anyone from Texas? So interesting. Oh, you see, is it true? Is it true that people say howdy in class and then everyone should say howdy?
Well, a little bit. It's a big Texas. A little bit. I only went elementary, middle. Definitely said howdy. So.
My friend, he's teaching at Texas University, yeah, and then Tamil, yeah. And he says when people are noisy, I just say howdy. Everyone immediately got quiet and say howdy back, and that's how he starts the class. So it's kind of funny. I was thinking if it's true or not. Dr. Payam, which we're using his notes. So that was pretty important. Let's see, tangent planes. And we keep going. We keep going for last 5 minutes with more stuff. Let's see. Tangent planes. We're going back to the topics we learned. Tangent planes. We learned tangent planes before. We're going back to cross product, normal vector, and that kind of stuff. There are 2 applications of parametric surfaces, and we're going to start with tangent planes. We need to learn how to find a tangent plane to a parametric surface, similar to what we did when we covered partial derivatives. For example, when you have a nice looking, let's just write down, find example. Find. I wonder what the phrase should be in Georgia. This. How you doing, y'all? The equation. Find the equation of the tangent plane. Tangent plane to the following. Why am I handwriting so bad? Following surface. Surface at. And now we're giving the other way around. We give you your u and we give you your v. That is a point. Because if you remember, which probably not is the case, The tangent plane is a plane. Plane can be created from a point and a normal vector. Remember we did something like this? How to describe a plane? A point and a sticking away normal vector. Then it describes the plane. So the point will be given with u and v. R of u comma v is given as, and now we're going to go the other way around. We're going to figure out what is this surface. Is it v? Yes, u squared plus 1, v squared plus 1, and then u plus v. And then build equation with tangent plane, normal plane, those kind of things, using parametric description of the surface. So it's x, y, and z, 3 coordinates, but it was described using 2 parameters, u and v. We need to find equation of a tangent plane. Remember, we were torturing you for tangent. Is this my tangent? We were torturing you with this phrase, find the equation of a tangent line, for literally 3 semesters, right? Calculus 1, 2, and 3. What was the very first step for all of those cases, no matter what dimensions we are at? Find derivative, right? In this case, let's do derivatives or slopes. So we find derivatives and slopes. What is the difference? Do you remember? Slopes are derivatives at the point 1 and 2. At 1 and 2. U and V are given. Derivative is a general differentiation. So we're going to do that. We're going to differentiate R. But wait a second, R depends on 2 variables. Wow, what should we do? Partial derivatives. R with respect to U and R with respect to V. Very fast. The answer will be a vector. That will be a tangent vector. Derivative with respect to U is 2U. With respect to V is with respect to U is 0 and 1. Agree? Everything with respect to U. The second one is with respect to V, 0, 2, V, and 1. And now, not to rewrite everything, the nice notation is at 1 and 2. At 1 and 2. What? The second one. Oh yeah, you're right. Did not write it down. My tablet is glitching. Yeah, I should probably restart it. In one of my classes, my tablet decided to upgrade the system for like 15 minutes. So now I'm afraid to restart it. I will do it after the class. Luckily, we had a quiz, so I just did not use it for 15 minutes. But it was very annoying. Plug 1 and 2, and you get a vector, which is 2, 0, and 1. And then 0, 4, and 1. So this is a point which will help us to figure out what is a tangent plane. Remember that R, U, and RV are on the tangent plane. So after this, we're going to find a normal vector. How do we do normal vector? Cross product. Cross product of what? R, U, and RV. And we need to review the cross product, but you're doing it right now in your homework, so it's fine. And so on. So we're going to continue with this topic next week. One more topic we have to do, and we are done with the whole semester.
No.
How exciting is that?
So sad.